A drop on your skin and the damage begins before you know it. A breath of invisible vapor and your body's control systems start to fail. Some of these compounds are engineered in labs, others exist in animals or even the soil, but all of them show chemistry at its most unforgiving. In this video, you'll see chemicals that burn materials most people think can't burn, chemicals that slip through the gloves meant to protect you, and chemicals still causing accidents in modern industry. Let's begin with one so dangerous even its original creators decided it was impossible to control. Chlorine trifluoride, the Nazi chemical too dangerous for Nazis. Chlorine trifluoride, or ClF3, was first synthesized in Germany in the late 1930s, when researchers considered it as a potential weapon. Even a regime already known for deploying poison gases and firebombing cities quickly abandoned it, not out of mercy, but because they realized they had created something even their own soldiers couldn't reliably handle. What makes chlorine trifluoride notorious is that it doesn't just poison or burn, it reacts with almost anything it touches. Most people think of fire as something that consumes wood, fuel, or fabric. This compound goes after materials most of us believe can't burn at all. Spill it on asbestos and the asbestos combusts. Drop it on a concrete floor and the concrete itself bursts into flame. Even ash, something that should be spent and inert, can reignite when drenched with it. It's one of the rare substances that makes fireproof a meaningless word. The only reason it behaves this way comes back to its chemistry. Chlorine trifluoride is one of the strongest known fluorinating oxidizers. It rips other substances apart at the molecular level, forcing reactions that oxygen alone can't trigger. To put it simply, it's a better oxidizer than oxygen. That means it doesn't wait for conventional fuel to burn. It supplies the drive needed to make stable compounds flare up, including brick, sand, or the residue of past fires. History has already shown how devastating this can be. In one mid-20th century US shipment, a storage tank ruptured and spilled a full ton of ClF3. What followed was not a typical chemical accident. The liquid burned straight through a thick concrete floor and then kept going, consuming nearly a meter of soil and gravel beneath it. Eyewitnesses could only describe it as though the foundation itself was ablaze. Unlike ordinary chemical fires that responders can smother, this one ended only when the last of the chemical had reacted away. And yet, despite being so unstable, it has found a foothold in modern technology. Semiconductor fabrication plants still use chlorine trifluoride in tightly regulated, highly automated systems. Its vicious tendency to attack anything in its path turns out to be an advantage for cleaning the inside of chambers where microchips are built. It removes microscopic traces of contaminants in ways that no other process can match. In this world, industries tolerate the hazard because the payoff is measured in faster, cleaner, and cheaper electronic components. That doesn't mean anyone takes the risk lightly. Safety agencies rank ClF3 among the highest risk chemicals still in commercial use. Containment systems are heavily engineered, workers are trained to treat even trace leaks as emergencies, and companies continue to update their handling protocols. Perhaps the most unsettling fact is that it can technically be stored in ordinary steel tanks. The chemical produces a thin protective film of metal fluorides on the inside of the container, a kind of armor that isolates the steel from the liquid. But that layer is fragile. One scratch, one crack, or an impurity that interrupts the coating, and the chemical immediately makes its presence known in the worst possible way. So chlorine trifluoride stands today as both indispensable and barely manageable, too unstable for weapons, yet too effective to abandon in high-tech manufacturing. It represents a balance between necessity and danger, tolerated only because strict control just barely keeps it in check. And although this substance shows how violently matter itself can burn, there are other compounds whose threat comes in a much more deceptive form, ones that don't set fire to the ground beneath your feet, but slip silently past the protections you trust most. Dimethyl mercury, the invisible killer that penetrates gloves. One of the most unsettling chemical threats doesn't announce itself with flames or explosions, but with absolute silence: dimethyl cadmium. This organometallic compound, once studied for its potential applications in research and industry, is now recognized primarily as a cautionary tale of extreme toxicity and instability. It looks like an ordinary liquid, yet its danger lies in how quickly it infiltrates the body and how devastating its effects are once inside. Dimethyl cadmium belongs to a class of chemicals where carbon atoms are directly bonded to a toxic metal, in this case cadmium. That bond makes the substance volatile, so it can evaporate into vapor you might inhale without realizing it. Once in the bloodstream, the compound distributes cadmium throughout the body in forms that are especially aggressive. Unlike cadmium dust or salts, which already cause serious chronic illness, dimethyl cadmium penetrates biological barriers faster, setting off acute damage in organs almost immediately. The toxic effects strike on multiple levels. The lungs suffer first when vapors reach them, but cadmium also damages kidneys and the liver while disrupting enzyme activity in cells across the nervous system. Acute exposures have caused rapid pulmonary irritation, chemical pneumonia, and systemic poisoning. At the same time, long-term cadmium exposure is already notorious for being carcinogenic, linked to kidney dysfunction, brittle bone disease, and cancer. Dimethyl cadmium magnifies these dangers by delivering cadmium in a far more reactive and bioavailable form. The molecule doesn't just linger passively in tissue, it spreads, binds, and cripples vital processes with ruthless efficiency. Even microscopic exposure can be dangerous. Legal occupational limits for cadmium compounds are measured in the millionths of a gram per cubic meter of air. Researchers familiar with organometallic cadmium notes emphasize that safety margins are so narrow that a misplaced droplet or unnoticed trace vapor could exceed permissible limits for an entire lab space. While the precise figures vary depending on regulation and country, the numbers cited in toxicology references make clear that only minuscule concentrations are enough to breach safety guidelines. It is not just the dose that makes the poison here. It is the pathway, speed, and the fact that no ordinary protective measures are sufficient once the compound is on the move inside your body. Adding to the danger, dimethyl cadmium is chemically unstable in ways that make laboratory handling even riskier. It reacts violently with water, producing heat and flammable hydrogen gas. A spill onto a moist surface or even humidity in the air is enough to spark hazardous decomposition. Compounds of this type are also known to form dangerous oxide or peroxide crusts during storage, residues that look inert but can detonate from friction or impact. In practice, this means bottles containing dimethyl cadmium become increasingly treacherous the longer they sit on a shelf. What began as a dramatic but manageable reagent can, over time, transform into something primed for catastrophic rupture. Historically, a handful of chemists pushed this compound into research use despite its well-advertised risks. Erich Krause, an organometallic pioneer, was among those who first investigated it. At the time, the dangers of cadmium itself were already becoming clear, yet dimethyl cadmium's mobility and volatility set it apart. Though small amounts were once explored as intermediates for semiconductor materials and other synthetic goals, its extreme hazard soon made it unworkable in practice. Laboratories quickly realized that safer alternatives could achieve similar reactions without threatening researchers, lives every time a container was opened. The chilling reality is how little margin for error exists in handling it. Respirators and protective masks cannot guarantee safety against small vapor leaks. Gloves or coats offer almost no meaningful protection if the substance is mishandled, since it vaporizes readily and spreads in air. Once a few molecules are inhaled, the process has already started, and the compounding cellular damage is extraordinarily difficult to stop. Unlike corrosive acids that leave clear burns or pungent fumes that signal immediate danger, dimethyl cadmium offers no instant warning. The exposed person may feel fine until cumulative damage suddenly manifests as a cascade of organ failure. Today, it stands less as a practical reagent and more as a demonstration of how not all rare or exotic compounds are worth pursuing. Regulatory agencies and laboratory safety boards have systematically restricted its use. Modern chemists are trained to recognize that some reagents, while scientifically interesting, are effectively off-limits for routine experiments. Few laboratories would even consider ordering it, and most working chemists know the name only from stories emphasizing its hazards, an academic ghost more than a living tool. The story of dimethyl cadmium underlines a brutal truth. Not every threat shows itself in flame, color, or smoke. Some chemicals exert their power through stealth, infiltrating tissues quietly and dismantling biological systems cell by cell. It is this invisible, inaudible assault that makes substances like dimethyl cadmium rank among the deadliest ever handled by human hands. And while chemicals of this type can slowly sabotage your body in silence, others pose an even greater paradox. They are so unstable that scientists struggle to study them at all, because they might erupt without warning before you even gather your data. Azidoazide Azide, the explosive that detonates when you look at it wrong. Azidoazide Azide is often described as the chemical that might explode if you so much as glance at it, and that's not an exaggeration. When it was first synthesized by a German research team in 2010, they reported that its sensitivity was beyond our capabilities of measurement. In other words, no standard test for stability could even be performed, because simply attempting to study it risked an immediate detonation. For a compound to earn that kind of description from experienced energetic material chemists tells you just how unstable it really is. The problem lies in its structure. Azidoazide Azide is an extreme high nitrogen compound, 14 nitrogen atoms crammed into one fragile arrangement. Nitrogen atoms, when given the chance, strongly prefer to exist as N2 gas, which is held together by one of the strongest bonds in chemistry, the nitrogen triple bond. In this molecule, nearly every atom is perched in a strained, unstable position, straining to break apart and release nitrogen gas. The moment a bond snaps, even from a trivial disturbance, the rest follow in a cascading collapse. The energy stored in those fragile arrangements all releases in a single instant, and the compound annihilates itself. What makes this different from other explosives is how little it takes to set it off, or rather, how little it takes for it to set itself off. Researchers noted that even tiny amounts could detonate when exposed to inconceivably small triggers, a change in light, brief exposure to X-rays, or sometimes nothing apparent at all. That unpredictability makes it impossible to treat with standard precautions. You can predict when dynamite or TNT will explode. With Azidoazide Azide, the only prediction is that if it exists long enough, it will eventually explode. Even the smallest attempts at storage have failed to provide stability. Imagine successfully isolating a fraction of a gram and sealing it carefully in glassware. Hours later, perhaps overnight, the container is found shattered, no fire, no applied spark, the material simply gone in a sudden pulse of chemical collapse. The destructive force in such tiny quantities is still sufficient to shred the vial and damage surrounding equipment. Researchers who attempted these early syntheses described the material as ready to destroy itself the moment it existed. Military interest in such compounds was short-lived. On paper, high-nitrogen explosives look perfect, lightweight, compact, with huge amounts of stored energy. But Azidoazide Azide demonstrated the fatal flaw of pushing that idea too far. The compound couldn't even survive the basic tests needed to classify it as usable. Chemists realized immediately that no army could ever transport or weaponize a material that obliterated itself in storage. The danger was not in how to deploy it, but in simply keeping it around long enough to deliver. The underlying instability comes from its repeating azide groups, chains of nitrogen atoms tied together in fragile links. Think of a room crowded with people desperate to leave. The moment even one door opens, the entire crowd surges outward, trampling everything in the process. Azidoazide Azide behaves the same way. Once one weak connection breaks, every atom rushes into the stability of gaseous nitrogen, and the release tears the whole structure apart. That urgency to disassemble means almost no detailed laboratory data exist. Normally, a chemist would study melting point, decomposition temperatures, or spectrum data. With this compound, tests often ended with destroyed instruments and shattered barriers. In many ways, computer simulations provide the only insight scientists have about its theoretical properties. The real material won't sit still long enough for careful measurement. It resists science itself in the most literal sense. Protective technology hasn't changed this reality. Remote handling arms, reinforced blast chambers, careful cooling protocols, none make the material safe enough to study on any meaningful scale. Its behavior hasn't softened with time or newer equipment. More than a decade since its first reported synthesis, it remains one of the most unstable molecules ever created. Even today, chemistry textbooks cite it not as a case study in application, but as an example of when chemical ambition goes too far. And yet, despite its impossibility, the compound continues to fascinate. At the time of its discovery, the German team cautiously described it as a very exciting discovery, but admitted it was far too touchy even to test properly. That blunt warning from the scientists who made it says everything. You may be able to make this molecule, but you cannot control it. For anyone handling it, the experience must have felt less like an experiment and more like living next to a landmine. So chemists remember Azidoazide Azide as a name, a warning, and little else. It stands as a reminder that not every structure we can design should ever exist outside a theory. Some chemicals destroy themselves before humans can even decide how to use them. And if some compounds threaten us with fire or instant shockwaves, others wield a danger that is far stranger. Rather than tearing matter apart, their weapon is something so intangible, yet so overpowering that entire neighborhoods have been forced to run from it in panic. Thioacetone, the smell that evacuated a city. In 1889, residents of Freiburg, Germany, experienced an extraordinary disturbance. There was no fire, no visible cloud, no chemical burns, yet people staggered into the streets, doubling over with nausea. Reports said the stench drifted for miles, sickening entire neighborhoods and driving large portions of the city's population to abandon their homes. The source was traced to a nearby chemical plant experimenting with a substance that would later gain infamy not for being lethal in the traditional sense, but for producing one of the most overpowering odors in recorded history. Its name was thioacetone. Thioacetone belongs to the group of sulfur compounds known as thiols, molecules instantly recognized by the human nose as the smell of decay. Skunk spray, rotten eggs, spoiled cabbage, all are thiols announcing corruption or danger. Humans can detect them in extremely small amounts, often just a few parts per billion. That sensitivity gave our ancestors a survival edge by warning them away from spoiled food. But thioacetone doesn't just trigger that system, it shatters it. Witnesses have described its odor spreading hundreds of meters from a single spilled drop and provoking violent reactions at distances that would normally seem safe. The accounts from Freiburg remain some of the starkest ever recorded. Entire blocks were overwhelmed by symptoms that went far beyond grimaces or wrinkled noses. People collapsed in the streets, vomiting and reeling from sudden dizziness. Others lost their balance completely, unable to stay upright after breathing and only faint traces in the air. Unlike toxic gases that silently damage organs after long exposure, thioacetone's effect is immediate. The smell alone destabilizes the body's reflexes, forcing headaches, nausea, and incapacitation within seconds. It turned an invisible emission into an event that residents still remember decades later. Additional experiments in the 1960s confirmed that this was not an isolated freak accident. Chemists in one European laboratory attempted to prepare thioacetone on a small scale, and even in quantities so tiny they barely filled a vial, the consequences spread throughout the facility. Workers in distant buildings, completely uninvolved in the experiment, quickly reported nausea and fled. The researchers abandoned their work midway. It was not worth continuing once they realized that just opening a flask would force colleagues several hundred meters away to evacuate their stations. Taken together, these rare episodes made one fact unavoidable: thioacetone is almost impossible to handle. Chemists who have faced volatile explosives, reactive oxidizers, and corrosive acids have still admitted defeat after encountering this compound. It doesn't blow apart a laboratory or dissolve equipment, but it makes any workspace uninhabitable. Attempts to confine it fail because ventilation systems cannot prevent its odor from traveling down hallways and through air ducts. Once airborne, its molecules spread so effectively that no localized containment seems plausible. The odor itself defies precise description. Some liken it to rotten meat infused with sulfur, others to sewage mixed with rancid vegetables. Yet all accounts agree that no analogy fully captures its effect. A human sense usually adapts to smells after a short while our noses fade background odors so we can detect something new. With thioacetone, there is no adaptation. The stench clings, intensifies, and dominates perception until physical illness forces retreat. Even seasoned chemists accustomed to foul reagents have called it the worst smell they have ever encountered. Because of this, thioacetone has remained a chemical curiosity rather than a substance with practical uses. While other thiols find applications in gas detection, pest deterrence, or training scent sensors, thioacetone is avoided. Journals document it only in scattered, reluctant reports, accompanied by confessions that the experiments ended faster than planned once buildings began to empty. For most laboratories, the risk outweighs any possible discovery. Researchers cannot justify clearing several city blocks just to analyze a sulfur molecule. Yet its extreme characteristics have fueled occasional speculation. Security theorists have asked whether compounds like these could serve as non-lethal deterrents, agents that cause chaos not by killing but by forcing people to run. Could a trace contamination protect secure sites, rendering them unbearable to trespassers? Could the chemistry that makes crowds gag be harnessed intentionally in small, controlled ways? Thioacetone itself is far too unpredictable and overwhelming for such roles, but the idea demonstrates how deeply its reputation has penetrated scientific culture. It suggests that even odor, normally dismissed as a nuisance, can become a weapon when pushed to extremes. Within chemistry circles, references to thioacetone are often tinged with humor, but that humor is uneasy. Researchers sometimes call it the ultimate weaponized stench, half-jokingly comparing it to a prank taken to apocalyptic levels. But beneath the laughter is a real respect for its disruptive power. No other compound is known to clear laboratories so quickly and forcefully. A simple whiff, even at a distance, has been enough to derail experiments, clear research complexes, or scatter a community without any visible cause. Today, thioacetone exists more as folklore than as a physical bottle in a storeroom. Students hear about it in classrooms as the archetype of unbearable odor. Safety manuals mention it when teaching about thiols and extreme odor detection limits. Documentaries and popular accounts return to Freiburg whenever they need to demonstrate the sheer force that smell alone can exert on human behavior. It is a textbook cautionary example of what happens when chemistry collides violently with biology's most sensitive alarm system. Unlike corrosive poisons or explosive materials, thioacetone's danger lies in its ability to make survival instincts unbearable. It immobilizes not through death but through disgust, and that contrast is what makes it unique. Scientists avoid it not because it can dissolve flesh or trigger combustion, but because one open vial can ruin entire laboratories and make people collapse blocks away. In the hierarchy of dangerous chemicals, it carves out a place as a different kind of menace, less about destruction, more about mass disruption. And if a compound famous for its smell can empty buildings, the next substance goes in the opposite direction. Instead of attacking our senses, it attacks the very materials we trust to contain it, showing that even glass itself can fail when chemistry pushes past its ordinary limits. Fluoroantimonic acid, the superacid that eats glass. Most acids corrode in predictable ways, burning skin, pitting metal, or eating through cloth. Fluoroantimonic acid stands apart because it does something so striking it borders on the unreal. It dissolves glass as though the container itself were nothing more than a temporary obstacle. Left in an ordinary beaker, the walls of the vessel begin to vanish, breaking down at the molecular level until the acid consumes the very material designed to hold it. For chemists used to handling dangerous substances, watching laboratory glass disintegrate in real time under its assault is a reminder that this liquid does not obey the usual hierarchy of hazards. To explain why, scientists place it in the category of superacids. These aren't just stronger versions of familiar acids like hydrochloric or sulfuric. A superacid means an acid so powerful that it outpaces conventional measures of acidity entirely. Where sulfuric acid is already vicious enough to char organic matter and scar whatever it touches, fluoroantimonic acid is many orders of magnitude stronger. A beaker of sulfuric might blister skin. This one annihilates it in less than a blink. The comparison is less about numbers than about scale. While a strong acid transfers protons with destructive efficiency, fluoroantimonic acid does so with unmatched force, forcing reactions to occur where chemistry would normally hold a line. What happens when it contacts living tissue is not simple corrosion. Organic molecules are torn apart at their skeletons, carbon bonds unraveled before the body has time to respond. Even the fluoride present adds a special danger. Fluoride ions react eagerly with calcium, and calcium is the structural backbone of bones. Where sulfuric acid might leave surface scars, fluoroantimonic acid can, in principle, attack deeper, undermining the very mineral lattice of skeletal material at the chemical level. Chemists who have studied its properties describe not just discomfort or thermal burns, but destruction extending down to the architecture of cells and bone. The mechanics behind this come down to its two parts: hydrogen fluoride mixed with antimony pentafluoride. Together they form a medium where protons are freed so aggressively that almost nothing resists them. Any compound unlucky enough to meet it finds its electron structure thrown violently out of alignment. What this means in practice is straightforward. Organic matter is reduced to fragments instantly, polymers are shredded at their core, and solids most people take for granted, such as glass, lose their structure as the assault continues. The phrase superacid is not exaggeration. It describes a proton generator so extreme that it rewrites the ordinary expectations of chemical reactivity. With this potency come severe limits on use. There are no factories producing it by the ton, no industries designing pipelines to carry vats of it. The quantities handled measure in drops, perhaps even smaller, and only within research settings where extreme transformations are required. Organic chemists sometimes need a way to shift bonds that normally resist every attempt at manipulation. A microgram of fluoroantimonic acid can force reactions others cannot. But no one pretends it has broad applications. Its value lies at the frontier of synthesis, where conventional tools fail and radical conditions are demanded. Few laboratories can justify working with it, and those that do treat even the smallest batch as a substance worthy of containment, bordering on paranoia. What makes that containment possible is a peculiarity of chemistry. Fluoroantimonic acid cannot attack Teflon. Teflon is built from carbon-fluorine bonds, among the most stable in chemistry, and so the acid finds no footing there. Containers made from this material hold it safely, which creates an ironic image. The coating that lines kitchen pans is also the only barrier strong enough to restrain the most formidable acid known. Store it in glass, steel, or most plastics, and the container would fail rapidly. Place it in a simple Teflon bottle, bright white and unassuming, and for once the acid is held at bay. Even though it sometimes serves a purpose in specialized experiments, fluoroantimonic acid's reputation looms far larger than its practical footprint. Students learn about it not as something they'll ever pour into a flask, but as an illustration of the extreme edges of chemistry, an acid so hostile to matter that even glass can't survive it. Seasoned professionals avoid it whenever possible, treating the idea of handling it as an unnecessary excursion into danger. The reality is that most chemists will never be in the same room with it. For nearly everyone, its role is symbolic, to remind us that human ingenuity can produce substances that stretch the very definition of reactivity. You can look at it from a very long distance and nothing more. Yet the lesson it delivers is lasting. Some substances earn respect not because they are used often, but because the thought of contact alone is enough. And while this liquid demonstrates how chemistry can surpass even glass in fragility, there are other remnants of human science that do not rest quietly in bottles or vials. They sit in silence, heavy and immovable, still radiating the consequences of past experiments long after the world thought the danger had ended. The elephant's foot, the smoldering remnant of Chernobyl. Beneath the ruined shell of Reactor 4 in Chernobyl rests a mass that became one of the most notorious legacies of the 1986 disaster. Hidden in concrete passages and dimly lit corridors, it came to be known by a grim nickname, the elephant's foot. In the first years after the meltdown, standing near it for even a short time was enough to receive a dose of radiation that could be lethal within minutes. The danger required no direct contact or inhalation. It radiated outward invisibly, devastating living tissue without smoke, flame, or warning. The name came from its unusual shape. When workers finally managed to glimpse it through remote cameras, they saw a rounded, rough surface like the creased skin of an elephant pressed into the floor. What they were looking at was not stone and not metal, but a new substance humans had never produced before. It formed when the nuclear fuel itself melted through the reactor, mixing with sand, concrete, and steel. This molten slurry, still burning at extraordinary temperatures, oozed into spaces beneath the core where it cooled into solid rock. Scientists later classified the hardened mixture as corium, and among all the flows created at Chernobyl, the elephant's foot was the largest, most stable, and most infamous. At its peak, the elephant's foot was so radioactive that even instruments struggled to measure it. Cameras sent into film often faltered, their images streaked and warped by radiation before their circuits burned out completely. Some of the robots deployed to examine it lasted only minutes before failing. Others broke down in place, left as wreckage near the mass. The foot resisted observation in a way that seemed almost deliberate. Every attempt to see it too closely ended with broken machines. For people, the threat was even clearer. In the late 1980s, exposure near the mass was quick and severe, leaving anyone who lingered facing acute radiation sickness. Symptoms could begin within hours: nausea, vomiting, and hemorrhaging, progressing rapidly toward collapse. The dose levels reported by specialists at the time were far above what the human body could endure. Scientists described it as one of the most dangerous solid objects created by modern technology, not because its surface burned or reacted, but because of the invisible radiation that flooded every square meter of its surroundings. Time has softened that intensity. By 2025, radioactive decay has reduced some of its most aggressive isotopes. Cesium, iodine, and strontium have diminished, lowering the radiation output by several orders of magnitude. Still, the elephant's foot remains hazardous. Standing near it unprotected is unthinkable, and researchers who study it must rely on shielding, dosimeters, and strict time limits. It no longer guarantees certain death in minutes, but it still carries enough radioactivity to steal health quietly from anyone careless enough to underestimate it. Decades have changed its appearance, too. Once molten and flowing, it gradually hardened into something closer to dark stone. Photographs show glossy patches that resemble glass, fractured edges that crumble at the surface, and fissures forming across its bulk from years of cooling. Beneath, it remains dense, solid, and radioactive. Corium continues to evolve chemically, too, as isotopes shift and break down within. The elephant's foot today is colder, cracked, and more brittle than in 1986, but its danger lies less in how it looks than in what still pulses inside. Ukraine, and to the world, the mass stands as a physical reminder of the price of Chernobyl. It is the accident made solid, a single block filled with uranium fuel remnants, fused metals, and countless unstable isotopes. Where the reactor's blast cloud spread fallout across Europe, the foot concentrated much of that chaos into one immovable object. Engineers see in it the outcome of technical failure and poor decisions. Society sees a symbol of nuclear power's risks made permanent. Its weight is measured not just in tons, but in generations of contamination it represents. The challenge of studying it continues. Even with protective suits and better equipment, researchers tread carefully. Attempts to bore samples or measure its stability require heavy shielding and remote handling. Small fragments have been removed and examined, but each act risks damaging the structure or scattering radioactive dust. Its surface crumbles over time, and experts monitor it for signs that it could collapse further. While entombed under layers of reinforced structures, the sarcophagus first, and later the massive new safe confinement arch, it still demands vigilance. A crack or fall could spread contamination into tunnels that today remain sealed away. Tourists who travel to the exclusion zone never get near it. Visitors are shown images, models, or photographs only. The real elephant's foot remains deep underground and is accessed only by a few specialists with clearance. To most of the world, it exists only as a haunting image, a frozen, blackened surface crouched beneath ruined concrete. Yet its existence has reshaped how humanity thinks about the long arc of nuclear disasters. It shows that when reactors fail, the results aren't just clouds of fallout but solid monuments of danger, resistant to time and physically inseparable from the land they scar. Its meaning is less about science now than about memory. It marks a moment when human ambition overstepped control, and the result could not be hidden or quickly undone. The elephant's foot still radiates not only particles but also history, reminding every observer that consequences of this scale do not fit human timelines. It forces the recognition that some mistakes remain dangerous for centuries. And while this relic of Chernobyl reveals how technology can leave behind hazards that imprison generations, there are other poisons far smaller, far lighter, and far more cunning. Instead of massive stone-like formations, they circulate as transparent molecules, quiet enough to vanish into a meal, yet brutal enough to silence the body in seconds. Tetrodotoxin, nature's tiny nerve blocker. Among the many natural threats that biology has produced, few capture attention like tetrodotoxin, best known from the Japanese pufferfish or fugu. This natural compound places dinner plates and science lessons uncomfortably close together, because inside the tissues of the fish lurks one of nature's strongest known nerve poisons. The toxin is so feared that Japan requires specialized training and licenses for chefs who prepare fugu. A single error, leaving even a trace of toxin, creates consequences far beyond what most foods could ever risk. Tetrodotoxin is striking not only because it originates in ordinary-looking sea creatures, but because of its efficiency. Some natural toxins are far more potent by weight than most man-made poisons, and this compound is one of the clearest examples. Where industrial chemicals often require measurable exposure before symptoms appear, tetrodotoxin needs only a vanishingly small amount to disrupt the body's core systems. Unlike acids that burn on contact or gases that overwhelm the lungs, this toxin works at the microscopic level, interfering directly with the signals that nerves use to control the body. The nervous system functions by sending electrical pulses along neurons. Those signals rely on tiny proteins called sodium channels, which briefly open to let sodium ions flow in and create a spark of electricity. Tetrodotoxin disables this system by slipping into those channels and blocking them completely. With the pathways obstructed, no signal can pass, no impulse reaches its destination, and muscle fibers never receive the command to contract. In essence, the body's electrical grid shuts down, one connection at a time. What makes its effect horrifying is the fact that the brain itself remains fully alert. Victims often report tingling in the lips and tongue at first, then spreading weakness as muscles go slack. As the toxin takes hold, voluntary movement fades. Eventually, even the diaphragm, the muscle that drives breathing, stops responding. The result is paralysis while consciousness persists. The mind continues to think, but control over the body is lost. In the worst cases, this leads to asphyxiation, where the body cannot draw in air even though the brain desperately signals the command to inhale. Scientists still debate the origins of the molecule within these animals. Evidence suggests that the fish themselves may not produce it directly. Instead, symbiotic bacteria living inside them could be the true source, with the host animal simply concentrating the toxin as a defense. This pattern has appeared in other creatures as well. The blue-ringed octopus, certain porcupine fish, and even some types of marine snails all carry the same compound. The common theme is survival. A predator that attempts to consume one of these animals faces sudden paralysis and death, an outcome that ensures the lineage of tetrodotoxin-bearing species continues. Human encounters with the toxin have been recorded for centuries, often as tragic stories of poisoning after eating improperly prepared seafood. By the 20th century, it became a subject of careful medical study. Researchers cataloged the symptoms and identified the stages of intoxication, confirming that the toxin targets sodium channels with precision unmatched by most known substances. Medical reports describe cases where patients could only be kept alive through mechanical ventilation for hours or even days until the toxin naturally cleared from the system. No chemical antidote exists. Survival depends entirely on maintaining basic functions until the body itself can slowly eliminate the compound. Modern Japan's strict regulations govern who can prepare and serve fugu. Chefs train for years, learning exactly which organs must be removed and how to ensure that the edible meat carries no trace of the poison. Restaurants capable of serving it advertise their chef's license as a symbol of both skill and responsibility. Even with this framework, only a small number of servings are permitted annually under government oversight. For the unlicensed or careless, the risks remain very real. Isolated incidents continue to remind the public that culinary daring can, in this case, be indistinguishable from recklessness. The paradox of tetrodotoxin is that its danger has also inspired medical curiosity. Because the toxin blocks sodium channels with exceptional accuracy, scientists have explored whether it could be repurposed in controlled doses for conditions like severe pain. If only a fraction of those pathways could be silenced, chronic pain might be reduced without the broad side effects of conventional drugs. Research in this area remains experimental, and the safety margin is razor thin. One too many molecules tips the balance from relief into paralysis. Yet the pursuit shows how even the harshest natural poisons can hint at possible therapeutic uses. For the public, though, the image of the toxin is shaped less by medical trials than by its distinctive cruelty. To remain conscious while the body falls silent has become a symbol of its uniquely terrifying power. Few other poisons allow the victim to understand fully what is happening and yet strip away every means of responding. The idea of a living person aware but immobile has made tetrodotoxin's reputation almost as legendary as its chemistry. What its story emphasizes is that evolution has had millions of years to refine chemical defenses. While laboratories can fashion acids, explosives, and industrial poisons, nature has already perfected compounds so elegant and efficient they exceed anything deliberately engineered. Tetrodotoxin is one of those reminders. A molecule shaped by biology, devastating by design, and effective at scales no factory production can quite match. Even so, not every deadly substance comes from natural evolution. Some are forged through nuclear processes and carry dangers of an entirely different nature. Unlike a marine toxin hidden inside a fish or octopus, these appear as invisible powders refined from reactors, nearly undetectable until the damage begins inside the body. Polonium-210, the assassin's element. Polonium-210 is often described as the ultimate assassin's element, a substance that turns ordinary dust into something capable of silently dismantling the human body from within. Unlike strong acids or engineered nerve agents, its weapon lies in radioactivity. Specifically, it is an isotope that emits alpha particles, a type of radiation both deceptively weak and devastating at the same time. Outside the body, alpha radiation poses little risk. The energy they carry is strong, but their range is tiny. Just a few centimeters of air or the outermost layers of skin are enough to block them. But once the isotope enters the bloodstream, that shielding vanishes. Every emission then occurs at point-blank distance within living tissue. Where chemical poisons interfere with single organs or pathways, alpha particles carve through DNA and proteins indiscriminately, destroying cells one by one. It's this contrast between seeming harmlessness on the outside and catastrophic damage within that has made polonium-210 notorious. The destruction begins at the cellular scale. Each alpha particle is massive compared to other forms of radiation, carrying far more energy. When they strike DNA, they break both strands at once, preventing repair. Proteins misfold or disintegrate and key cellular machinery collapses. The isotope distributes unevenly across the body, with especially high activity in the liver, bone marrow, and digestive tract. Those tissues then experience acute radiation injury, bleeding, immune failure, and exhaustion of the body's ability to regenerate cells. Victims experience the full cascade of radiation sickness, nausea, hair loss, hemorrhaging, and organ failure, advancing relentlessly over days or weeks. There is no antidote, only palliative attempts to prolong survival. What makes it especially insidious is its form. In powdered or salt states, polonium-210 appears like ordinary dust. It has no smell, no taste, and no ability to irritate the mouth or throat. Traces mixed into food or drink would escape immediate detection, carrying only subtle warning signs as poisoning progresses. Specialized nuclear detectors can identify contamination, but they are rarely present outside scientific or security contexts. To the unaided eye, it is indistinguishable from harmless materials, which is precisely what gives it such chilling reputational weight. Its rarity only deepens that aura. Polonium-210 does not exist in usable amounts in nature. Tiny traces occur in uranium ore, but they are orders of magnitude too small for practical use. To obtain it in measurable quantities, it must be engineered in nuclear reactors, typically by bombarding bismuth with neutrons. The process yields only minute amounts even under controlled conditions, and extraction itself demands specialized facilities. What this means is that access to the substance is effectively confined to state-level programs. The notion of an individual casually obtaining or using it is unrealistic. It requires infrastructure, funding, and security on the scale of governments. That exclusivity explains why polonium is associated less with battlefield weapons and more with intelligence operations. Possession alone reveals the involvement of highly resourced actors. Its scarcity, combined with the level of expertise required to manufacture it, effectively rules out ordinary crime. This explains its particularly sinister reputation as a tool of secrecy. Its presence implies intent, planning, and access to the kind of production only national programs maintain. The severity of its effects are hard to convey in everyday terms. A fraction of a milligram, amounts invisible to the naked eye, can be enough to ensure death. That tiny mass contains trillions of radioactive atoms, each emitting particles that unleash irreversible molecular damage. Most poisons work in milligrams. Polonium-210 is measured in curies of activity instead, borrowing a scale from nuclear physics rather than toxicology. It takes almost nothing to overwhelm a human system, which is why the material is handled under strict shielding even by those who create it. Handling polonium is nearly as dangerous as being its target. Scientists preparing or storing it must work behind heavy protective barriers, not just because of its emissions, but because powdered particles can spread invisibly through air. Facilities capable of containing it use thick glove boxes, sealed chambers, and remote handling tools. Even then, accidents can leave measurable contamination. The isotope's own half-life of about 4.5 months also means it diminishes steadily, releasing powerful radiation as it decays. For security agencies, this makes it both useful and unnerving, a substance that cannot be stockpiled indefinitely but delivers immense power while it remains potent. In public discussions, polonium-210 often symbolizes the extreme end of silent poisoning. No odor, no taste, nothing visible to the untrained observer, yet progression toward death almost guaranteed once it enters the body. Its very identity as a radiological poison sets it apart from chemical toxins. Where acids corrode visibly and explosive materials announce their presence with fire or shockwaves, polonium works invisibly and implacably. Its threat isn't dramatic in the moment of use, it's in what unfolds quietly inside a victim over days, while external evidence is scarce. Though accounts of its use remain rare, its impact on global awareness has been outsized. It's invoked in security discussions precisely because it is not widespread. The combination of nuclear science, invisibility, and absolute lethality ensures that it remains infamous whether or not it is ever actually deployed. In that sense, polonium-210 is as much a symbol as a material, a reminder that the tools of modern science can produce poisons unlike anything encountered in nature or conventional warfare. Modern investigators acknowledge that rare isotopes like polonium present unique forensic challenges. Tracing small amounts can sometimes link material to state-level production facilities, which complicates its use in secrecy. Still, those efforts cannot undo the effects inside a body already exposed. Once alpha radiation begins its work in tissues, no tool currently available in medicine can reverse it. All that remains is to watch the rapid breakdown of organ systems as the isotope continues to fire particle after particle into cells. That is why polonium-210 is remembered less for quantity and more for quality. The quality of its radiation, the precision of its lethality, and the certainty of its progression once introduced. It illustrates how nuclear physics, when turned inward onto the human scale, produces devastation that no chemical alone can match. Silent, selective, and scarce, it endures as the archetypal poison of covert conflict. And while this isotope embodies death delivered in microscopic doses, some radioactive byproducts leave their mark in far larger ways. Instead of being hidden in a sip of liquid, they drift into the air after disasters, settling into soil and muscle alike, and casting a shadow that lingers for decades. Cesium-137, the lurking fallout hazard. When nuclear fuel breaks down, one of the most concerning remnants is cesium-137, a radioactive isotope that has come to symbolize the problem of long-lasting fallout. You can't see it, you can't smell it, and you can't taste it, but once it's in the environment, it can remain for decades. Unlike gases that dissipate quickly, cesium stays behind in soil and water, where plants and animals can unknowingly pull it into the food chain. Cesium's danger begins with its chemistry. On the periodic table, it sits close to potassium, an element our bodies depend on to fire nerves and contract muscles. Cells are constantly taking up potassium from the bloodstream, pulling it into tissues where it keeps the body's electrical systems running. Cesium is close enough in size and charge that the body mistakes it for potassium. That means cesium isn't filtered out efficiently, it's absorbed, distributed, and stored inside living tissue. Once there, cesium-137 emits radiation from within the body itself, delivering slow, continuous damage that raises the risk of cancers and other long-term illnesses. Unlike substances that burn or corrode visibly, cesium quietly accumulates. Small amounts circulating in an environment can eventually be found in crops, grazing livestock, or fish. Once those pathways are in play, the isotope passes hand to hand, from soil to plant, from animal to person. This persistence is one of the primary reasons certain radioactive isotopes released in reactor accidents continue to trouble communities years later. Even as memories of an accident fade, cesium can still be present in the fields and forests, silently pulsing out gamma rays. One of the defining features of cesium-137 is its half-life. Every radioactive isotope decays at a predictable rate, and cesium's clock runs on 30-year intervals. In practical terms, if an environment is contaminated, the hazard is not brief, it stretches across generations. 30 years later, only half the atoms will have decayed. After 60 years, a quarter still remain. This timeline builds a legacy that must be managed long after the original release. Farmland, rivers, and even urban landscapes can all remain off limits, not because of flames or toxins, but because of this slow, numerical march of decay. The way cesium emits radiation makes it dangerous even in small quantities. Gamma rays produced by its decay can travel through the body and strike deeply buried cells. Unlike alpha particles, which stop at the skin, or beta particles with limited range, gamma rays penetrate, affecting every layer of tissue. That means external exposure is harmful, and internal exposure is even more severe. Once ingested, there is no reliable way to remove it completely. The body has to metabolize and excrete it slowly, often leaving damage behind during that process. Some isotopes are frightening because they unleash instant violence. Cesium-137 is frightening because it combines subtlety with endurance. The contamination doesn't shout, it lingers quietly. A few grains of contaminated dust in the wrong place are enough to trigger alarm in health inspectors and force costly interventions. Soil layered with it must be scraped, bagged, and stored. Water supplies require monitoring. Diets in affected regions face years of restrictions. The burden on those living nearby is measured not in moments of panic, but in decades of watchfulness. Accidents throughout nuclear history have shown how troublesome cesium can be once it escapes controlled systems. While other isotopes fade quickly after a reactor shuts down, cesium remains one of the dominant sources of hazard for years, sometimes decades. Governments tasked with cleanup face the scale of moving Earth itself, literally tons of soil shifted from one place to another to try and lower exposure. Even then, hidden particles often turn up in unexpected corners, reintroducing contamination after areas were declared safe. It becomes a cycle of rediscovery, underscoring just how hard it is to ever call the problem finished. The isotope attracts particular attention in discussions of nuclear security because it is relatively common in radioactive waste. That abundance makes it a long-term management challenge. It is not exotic, rare, or fleeting. It exists in appreciable amounts and therefore demands constant oversight. Storage sites must be designed to withstand leaking, corrosion, and shifting geology for centuries, because cesium will still be emitting long after its original creators have passed away. For communities near those sites, that responsibility doesn't feel abstract. It shapes planning, property values, and the very sense of identity tied to living alongside nuclear material. There is another unsettling aspect, too: the way cesium-137 appears. Sealed into glass or metal containers in laboratories, radioactive isotopes can look deceptively harmless. To the naked eye, there is no signal of danger, no odor, no smoke, no corrosion. That absence of warning signs has led to tragic outcomes in the past when people encountered unsecured medical or industrial sources. Unlike brightly colored poisons or acrid gases, cesium disguises itself as something inert. The threat becomes clear only after exposure, when radiation has already marked its victims. Because of all these factors, cesium-137 has become a symbol of how nuclear byproducts outlast human timelines. It embodies the trade-off at the heart of nuclear power: immense energy on the one hand, immense stewardship on the other. A reactor can produce power for years, but with it comes a residue that will require attention for centuries. Each gram stored away is a small promise passed forward to the next generation, that they too will keep watch and ensure it remains confined. It is not just a chemical problem, but a social one, blending science with politics, economics, and trust. This isotope teaches a lesson that applies beyond nuclear science. Some of the world's most dangerous substances do not work through shocks or drama. They work because they wait. They persist past the headlines of disasters and force societies into long struggles with monitoring and remediation. There is nothing cinematic about cesium-137 sitting quietly in soil, yet its quietness is exactly what makes it a challenge. It represents danger that is invisible, enduring, and woven into the ordinary landscapes where people live. And as we've seen, some hazards are measured in decades and tonnage. Others, however, are lethal for a far different reason, because a single molecule in the wrong place can turn the body's vital systems off like a switch. Botulinum toxin, the deadliest poison and a beauty treatment. Some toxins stand out not just for their raw power, but for the strange double lives they lead. Botulinum toxin is one of the clearest examples, a biological poison recognized as the most potent substance known, yet also the foundation of a multi-billion-dollar medical and cosmetic industry. In one context, it represents an almost unparalleled hazard. In another, it is delivered to patients every single day in carefully measured doses. That contradiction, poison and treatment contained in the same molecule, is what gives botulinum toxin such a striking place in discussions of dangerous substances. What makes the toxin so effective is how it interferes with the most basic communication between nerves and muscles. Normally, nerve endings release a chemical messenger called acetylcholine whenever the brain signals a muscle to contract. Botulinum toxin blocks that release. It disrupts the proteins that carry small packets of acetylcholine to the surface, preventing the messenger from being delivered. The nerve still fires its electrical signal, but the muscle never hears the command. What follows is paralysis, muscle fibers that remain limp, not because the muscle itself is damaged, but because it never receives instructions in the first place. The scale at which this happens is difficult to comprehend. Most poisons need measurable amounts before symptoms appear. Botulinum toxin is different. Even extraordinarily small quantities are enough to trigger paralysis severe enough to halt breathing. Scientists describe its potency in nanograms, fractions of a billionth of a gram, because any larger measure feels too crude. These vanishing quantities are the reason it is consistently labeled the deadliest poison by weight. While other compounds may burn, corrode, or suffocate at higher doses, none rival the efficiency of this toxin in silencing the nervous system with so little. That reality could make botulinum toxin nothing more than a terrifying footnote in toxicology, a chemical to be avoided at all costs. But medicine saw something else in its mechanism. Because it paralyzes with accuracy and duration, doctors learned to adapt it into therapy. In cosmetic procedures, tiny dilutions are injected under skin to relax the small muscles that crease with age. Where those fibers lose strength, wrinkles soften. For millions of people worldwide, the poison that could devastate the body becomes a routine tool to smooth facial lines. The same principle extends to treatments beyond appearance. Neurologists use it in controlled settings for conditions involving involuntary contractions, like spasticity after strokes or chronic migraines where muscle tension plays a role. Ophthalmologists apply it to stubborn squinting disorders. Urologists investigate its role in calming bladder overactivity. In every case, success comes not from avoiding its dangerous effect, but from steering it toward a specific target with extreme precision. Here, what would otherwise be catastrophic becomes profoundly helpful. This balance, deadly in one setting, therapeutic in another, depends entirely on dosage and control. The amounts used in medical settings are diluted to levels billions of times weaker than what would be lethal. Professionals administering them operate under strict training and guidelines, treating each injection as a calibrated act of restraint. Patients often never consider the scale of this distinction. For them, it is a practical procedure producing visible results, not a brush with the molecule once classified as a potential bioweapon. Yet behind every syringe is the simple fact: it contains the same agent toxicologists place at the pinnacle of lethality charts. The dual image of botulinum toxin, that 1 milliliter in the wrong place could be a national security concern while microliters in the right place become routine, illustrates how flexible scientific context can be. It unsettles people when they realize a cosmetic filler is chemically identical to a substance governments monitor as a potential weapon. But it also underlines how much of modern medicine is built on turning risks into benefits, transforming poisons into prescriptions. Digitalis, arsenic derivatives, and controlled radiation have all made the same transition. Botulinum toxin is simply the most extreme case. What remains striking is how normal its medical side has become. Clinics advertise wrinkle reduction openly, with bright billboards and casual messaging, while academic papers highlight new therapeutic routes. For many patients, it feels no more unusual than taking antibiotics or painkillers. Yet professionals in toxicology continue to regard it with caution, reminding anyone listening that beneath the routine lies the deadliest known toxin waiting for context to decide its role. The molecule itself hasn't changed. It is human choice that makes the difference between medicine and catastrophe. As with many dangerous substances, the story of botulinum toxin is less about the molecule itself and more about the razor's edge of human control. The toxin draws a clear line between benefit and disaster, therapy and threat. It is a reminder that progress often exists side by side with risk, and that our willingness to balance those two shapes much of what is possible in science and medicine. And while this particular poison demonstrates how context can flip a lethal agent into a therapeutic tool, there are other substances built with no such balance. Some were designed to harm from the outset, crafted not for healing or utility, but as weapons meant to disable entire populations within moments. Sarin, the gas that shuts down nerves. Sarin is the name that turned nerve agent from abstract military jargon into something ordinary people fear. Known to chemists as an organophosphate compound, it is designed not to burn, corrode, or leave visible marks, but to short-circuit the body's ability to breathe and move. What gives sarin its reputation is how quickly it interferes with life's most automatic functions, overwhelming the nervous system long before there is time to react. At the molecular level, sarin targets a simple but vital chemical circuit. Normally, muscles contract when a nerve releases a messenger chemical called acetylcholine. Once that signal is received, another enzyme, acetylcholinesterase, clears away the messenger instantly, allowing the muscle to relax. This switch-on, switch-off rhythm is what makes breathing rhythmic and movement fluid. Sarin blocks that enzyme. The messenger molecule builds up uncontrollably, and the switch that was meant to flick off stays jammed in the on position. Muscles seize into unrelenting tension, locked on command without reprieve. The symptoms arrive almost immediately. First come blurred vision and uncontrollable watering of the eyes, quickly followed by drooling or difficulty swallowing. Soon the muscles twitch and burst before ceasing altogether. Breathing grows strained as the chest muscles harden into spasm. With the diaphragm locked, no fresh air can be drawn in. The victim remains conscious through much of this, acutely aware of suffocation yet unable to override the chemical flood. Unlike poisons that creep through the bloodstream slowly, sarin's damage unfolds in minutes. Part of its dread is speed. A trace inhalation can trigger signs in seconds, and the window for intervention is narrow. Medical professionals focus on blocking the excess signals and supporting breathing, but treatment is only possible if help arrives almost immediately. Survival is measured in whether the body can be kept alive long enough for any intervention to work. There is no drawn-out progression. Sarin's hallmark is abrupt collapse. On the battlefield, its physical properties compound the danger. As a liquid, it can be stored or transported with relative stability. Once dispersed, it turns into vapor invisible to the eye with little odor at concentrations that cause harm. Victims often have no warning until their vision blurs or their chest clenches tight. In this way, sarin differs from fire or explosives. It leaves buildings intact while disabling the people inside them. A few liters, if vaporized effectively, can affect entire groups. For military planners, that potential made Sarin a textbook area denial weapon, an agent that does not destroy structures but renders space uninhabitable. The invisibility of exposure worsens the hazard for emergency response. Soldiers or civilians may not realize they've been contaminated until the symptoms have already begun. By the time first signs appear, precious minutes have been lost. Protective masks and suits reduce the risk, but their use depends on knowing an attack has occurred. For the unprepared, Sarin's lack of taste, smell, and color makes recognition nearly impossible until the compound is already inside the body. Efforts to restrict chemical warfare have long centered on agents like Sarin. International conventions ban its possession, production, and use, with inspections and destruction campaigns aimed at removing existing stockpiles. Yet history shows that once a technology is introduced, eliminating it completely becomes extraordinarily difficult. Nerve agents are chemically simple enough that determined programs can reproduce them, and secrecy makes enforcement uneven at best. Decades after its creation, reports continue to surface concerning hidden reserves. Even a small amount hidden away is enough to raise global concern because the risk scales so quickly from a drop to a mass casualty threat. For those studying its mechanism, what stands out is not flamboyant destruction but silence. Victims collapse without external wounding, their bodies paralyzed by signals that won't switch off. What unfolds looks from the outside like sudden loss of strength, but is in fact the body fighting its own locked-in biochemical loop. The cruelty lies in the awareness victims often retain while their essential muscles freeze, and the helplessness of watching ordinary movement shut down step by step. That cold efficiency is the mark Sarin left on the world, a compound that by exploiting a single enzyme turns the nervous system into an unyielding trap. Its design strips away choice, the body obeys chemical command until life halts. And while Sarin is remembered for its speed and invisibility, there exists another agent in the same family more disturbing still, not because it strikes faster, but because it refuses to disappear once released. VX nerve agent, the most persistent poison gas. VX occupies a unique category among chemical weapons, remembered less for sudden catastrophe than for the relentless threat it leaves behind. Unlike volatile agents that evaporate or break down within hours, VX persists. It clings to surfaces, lingers on clothing, and seeps into soil. A droplet deposited on metal or concrete resists weather and cleaning, retaining its lethality for days or even weeks. Its presence transforms ordinary terrain into an active hazard. In military terms, it does not just pass through a battlefield, it turns the ground itself into a weapon. Chemically, VX operates on the same principle as other nerve agents. It targets acetylcholinesterase, the enzyme whose role is to clear acetylcholine from nerve junctions. Without that clearing mechanism, the neurotransmitter accumulates unchecked, constantly forcing muscles to contract. Normal bodily functions, walking, blinking, breathing, all depend on cycles of contraction and relaxation. VX blocks the release cycle, leaving the body locked in spasms. Most critically, the diaphragm cannot relax, meaning the chest cannot rise for the next breath. Within moments, the nervous system is overwhelmed and asphyxiation follows. What sets VX apart is not the mechanism itself, but the stubborn way it endures after application. In gaseous form, it can contaminate a closed space for hours. In liquid form, it behaves like oil, adhering to surfaces and resisting cleanup. Ordinary washing does little, often spreading the residue further instead of removing it. Pamphlets prepared for soldiers highlighted this persistence as the defining danger. Once VX covers ground, that space becomes unusable without protective equipment. In effect, the environment itself is poisoned, denying entry even to advancing forces. Its potency compounds that persistence. Effective doses are measured in micrograms. On bare skin, a droplet smaller than a pinhead is enough to cause muscle seizures and respiratory failure. Inhalation requires even less. Symptoms appear rapidly, beginning with blurred vision, nausea, and watery eyes before escalating to full convulsions. Unlike substances that accumulate slowly or demand large exposures, VX works at scales too small to see. Military analysts once emphasized that entire units could be disabled by quantities smaller than a household bottle of medicine. For operational use, this combination of persistence and potency defined its role. Military planners envisioned shells or bombs releasing VX not to demolish infrastructure but to immobilize ground itself. Armored vehicles, tanks, or supply depots could remain intact yet unusable, trapped behind invisible contamination. Soldiers would hesitate to cross areas suspected of exposure, creating zones no one could hold or reclaim. This area denial tactic made VX uniquely destabilizing compared to faster fading agents. Where Sarin presented an acute crisis, VX represented occupied territory with no visible opponent. The international response acknowledged that distinction. Treaties banning chemical weapons focused especially on VX, recognizing the destabilizing effect it would have if deployed widely. Large-scale production facilities once existed to create war stocks, but their risk eventually outweighed any strategic advantage. The threat was not just in wartime use but in storage itself. Batches could last for years, raising fears about accidents, theft, or hidden caches. Modern arms control has sought to identify, dismantle, and neutralize remaining supplies, though suspicions about undeclared stockpiles persist. Even in small amounts, VX presents severe challenges for detection and decontamination. Its lack of smell or color means victims receive no warning until symptoms start. On surfaces, it resists evaporation, meaning a contaminated object can pose danger long after the initial release. Decontamination crews trained during the Cold War emphasized that protective suits, sealed equipment, and chemical neutralizers were essential. Even then, small traces could complicate cleanup for days. For civilian populations, this persistence would magnify chaos. Streets, homes, or public transport touched by VX could not be reoccupied safely without extensive remediation. The influence of VX extends beyond battlefield strategy. Security agencies discuss its potential in terrorist scenarios not because vast industrial quantities are needed, but because a few milliliters could disable entire enclosed spaces. Its oil-like consistency allows it to be spread on surfaces unobtrusively, and its lack of immediate irritation means victims rarely notice until the effects cascade. While explosives announce their destruction instantly, VX delays recognition until individuals collapse, giving little time for escape or intervention. Scientific monitoring continues to track signs of VX activity. Specialized satellite imaging and environmental analysis can reveal traces at suspected facilities. Even the slight contamination left in soils or vegetation can indicate preparation. The persistence that gives VX its battlefield strength also leaves behind footprints visible to forensic scrutiny. That makes it both feared and in some ways more traceable than faster-acting compounds. Authorities treat any possibility of its presence as a crisis requiring immediate verification, knowing how difficult cleanup would become if even a small release occurred. What stays in focus is the chilling efficiency of the agent. It requires no dramatic releases, no conspicuous clouds. A few unnoticed drops on a doorknob or handrail could be enough to affect dozens of people. Scenarios like this are part of why VX became an enduring symbol of chemical warfare, not for its speed but for its lingering silence. It demonstrates how a battlefield, a street, or even a single object can be transformed into a carrier of death without leaving visible marks behind. Today, VX is remembered less through deployment than through its reputation. It represents the concept of persistence weaponized, where material reality itself becomes hostile long after conflict ends. Unlike explosives which strike and fade or volatile gases which disperse, VX forces recognition that the fight does not stop when the release is over. The environment itself remains unsafe, denying habitation, progress, and even ordinary routines. Among nerve agents, VX still sits at the peak of dread because it embodies contamination made permanent. It does not announce itself with smoke or fire, but with the realization that a location may never again be trusted. In this way, its danger is measured not just in lives lost, but in places abandoned, terrain marked as unusable, and the enduring fear of invisible residue. And after considering such a weapon, lethal for how it lingers, the discussion turns to a very different kind of chemical threat. Not everything deadly works by collapsing the body in minutes. Some operate on a slower clock, embedding themselves quietly into life's routines and reshaping health over years rather than moments. Aflatoxin B1, nature's cancer-causing molecule. Among naturally occurring poisons, some of the most troubling are the ones produced by common molds that grow unnoticed on food. Aflatoxin B1 is one such toxin found in contaminated grains, corn, and peanuts stored in warm, humid conditions. Unlike fast-acting poisons, its danger accumulates quietly. When eaten, the liver converts it into reactive compounds that damage DNA, a process strongly linked to the development of liver cancer. What makes it unsettling is that contamination can hide in everyday diets, with low doses repeated over years creating irreversible harm. These slower chemical threats remind us that danger doesn't always arrive suddenly. If you want more of these hidden chemical mysteries explained, remember to subscribe and share your thoughts in the comments.